All right, morning everyone. So yeah, I've been tasked with keeping you awake for the next 50 minutes before morning tea. So hopefully I can do that with a few pretty pictures. I probably should have included a few more or some videos or something to, but I'll do my best. So I'm going to give a kind of whirlwind overview of severe convective storms. Just to highlight this, so this is a photo of a storm. This was just a couple of weeks ago in Wyoming. Which is actually a bit unusual to have a storm like this in such high terrain. But this was taken by a friend of mine who I went chasing with in the US a few years back now. And I think unusually he and the guy he was with were the only people on this storm. Storm chasing's become a big thing in America, and often there's actually traffic jams on the road because there's so many people chasing storms. But they were one of the only people who got this, and you might find well, they got a write-up in the Daily Mail, which is a terrible, terrible newspaper, but it's pretty cool. So I'll be talking about these tornadoes and some other exciting weather hazards. So just to outline what I'm going to be going over, so I'm going to start off, go through some sort of basics, try and make sure everyone's on the same page in terms of sort of basic dynamics of convection, thermodynamics. And then I'll talk a bit about the initiation and then the organization of convection before I actually get on talking about the different hazards. And yeah, throughout this, please feel free interrupt or ask questions throughout if you have any. And at the end, I'll go on and I'll try and make this all a bit more relevant and talk about these storms in Australia. I think a lot of the literature in this area is very US-centric, and you'll see that from a lot of my figures. I'll try and highlight when things have to be flipped for the Southern Hemisphere. That's because there's a lot of places that do research in that, but as I'll show you, these things do occur in Australia, and they are a big deal here. And I'll finish up by talking a bit about how climate variability and climate change may be influencing these types of events. Okay, start off with a few really basic definitions. What is convection? Well, this is the AMS Glossary definition. I think it's important to point out that in atmospheric science, convection is used in a slightly different term from more generally in kind of physics. So I think in physics in general, convection is any kind of movement that involves the transfer of heat, so that could be advection or diffusion. But in the atmosphere, we're really talking about vertical overturning of the atmosphere, and it's really that which is associated with the effects of gravity. And I'll explain more what this means on an unstable vertical distribution of mass. It's basically associated with buoyancy. Yeah, but this is what convection is. Anything from your sort of typical fair weather cumulus up to towering cumulonimbus storms. But these are the ones we're interested in here, really. And so from the point of view of a severe convective event, this is a definition that's fairly universal. So this is what the Bureau defines as a severe convective storm. So one which produces one or more of large hail, bigger than 2 centimeters in diameter, strong winds. A tornado of any intensity is considered severe, perhaps unsurprisingly. And then finally, I've also included, the Bureau also includes heavy rainfall that's conducive to flash flooding. I've put these stars here just to indicate, in the US, when they talk about severe convective storms, in other places, this is often actually left out, and it's not to suggest that it's not important, because it really is. In terms of fatalities, flash flooding far outweighs all of these other hazards. But the issue with flash flooding is that it's not just a meteorological event. There's a big hydrological component to whether a particular amount of rainfall will produce a flash flood. So things like whether the ground's already saturated, the characteristics of the drainage basin, things like that. Whereas these other events, it's really all down to the meteorology. So it's worth highlighting that there is that difference there. Oop, skipping ahead. Okay, yeah, so to understand the real fundamental basics of convection, you want to start with the vertical momentum equation. So some of you may be familiar with this, maybe in a more complete form. Here we've neglected things like friction, because we're mainly interested in what's going on above the boundary layer where friction really matters. We've neglected the Coriolis force because we're looking at scales where the Coriolis force isn't really important. We're talking about the scale of an individual convective updraft. So that doesn't really matter. So basically, what this says is that accelerations, vertical accelerations, are associated with two effects. And we can make this a bit more intuitive if we define ourselves a background state which is horizontally homogeneous, so it's uniform in the horizontal, and that is in hydrostatic balance. And if you do that and you plug that into this equation, you get this form of the vertical momentum equation. And this is kind of really sort of fundamental equation for convective dynamics. So it says that accelerations, vertical accelerations, are the result of two processes. This term here, which is known as the buoyancy term, so basically what this is saying is that if you have a perturbation in density which is negative, so you have a blob of air that is less dense than its surroundings, then that's going to contribute a positive acceleration, which is what these figures show. And vice versa, if you have a positive density perturbation, then you're going to get a downward acceleration. And then we have this other term that's thought about a bit less, but is really critically important in thunderstorms like the one I showed on my first slide. And this is vertical perturbation pressure gradients. So many of you will be familiar with the idea that pressure gradients drive the wind, and we often think about in the horizontal in terms of like the geostrophic wind. But this is important in the vertical as well. So if we have some sort of a pressure perturbation which decreases with height, so you've got a lower pressure perturbation above a higher pressure perturbation, then that's going to create an upward acceleration as well, and vice versa. And I say this is a really important process in supercell thunderstorms, which I'll talk about a little bit later. So those are the two processes, but for the most part, we're really going to focus on buoyancy because this is the thing that drives most convective processes. So yeah, so focusing on buoyancy then, we can change this expression a little bit. We don't tend to think too much in terms of density, we tend to think in terms of temperature. So what you actually find is that buoyancy is given by the gravitational constant times by the perturbation virtual temperature over the background kind of mean virtual temperature. What this is just saying is that if a parcel of air has a positive virtual temperature perturbation, it's essentially warmer than its surroundings, it's going to want to rise, right? And you can actually express this more clearly by taking this as the difference between the parcel's temperature and its surrounding environment. So I think this is a really nice way. And just to clarify, the virtual temperature is just temperature taking into account the fact that when you've got moisture in the air, it makes the air less dense. That's all it is. So that's what this equation at the bottom here shows. It's just the temperature multiplied by this factor, which includes the mixing ratio. So there's another effect here as well, and this is particularly important when we think of downward movement in thunderstorms. And this is what's called the hydrometeor loading term. So if you have your parcel of air contains raindrops or hail and other things like this, and they're falling, then this exerts a sort of drag force on the air. And this adds an extra term into the equation. So here we've got the hydrometeor mixing ratio. So this is just, essentially the mass of rain, snow, hail, etc. that's contained in your sort of arbitrary blob of air. So a few other important definitions. I've already mentioned some of these terms. So yeah, updrafts and downdrafts. There's an important distinction to make here. So your updraft is, your central buoyant rising part of a convective storm, or convective cloud, I should say more generally. Generally associated with positive buoyancy, but there may be a component due to this perturbation pressure field I mentioned before. But then the downdraft, this is the, as we'd expect, the downward part of the storm, but this is actually associated with things like evaporation of rain and that hydrometeor loading I mentioned before. This is distinct from the fact that you've also got some sort of compensating subsidence in the environment. So you've got this rising plume. Around it, in the sort of larger area around the cloud, you've got generally slightly descending air. But that's not what we're talking about when we talk about the downdraft. The downdraft tends to occur in the low levels of the storm and is associated with the fact that you've got this kind of weight of water and ice in the cloud that's sort of dragging air downwards, and then also processes like evaporation. And yeah, so Another few terms that I want to make you familiar with is cold pools and outflow boundaries. So your downdraft's descending from the storm. When it reaches the surface, obviously it can't pass through the surface, so it spreads out. And it takes the form of what's known as a density current. Some of you may have seen sort of laboratory experiments with a tank where you release a dense fluid and it spreads out. And this sort of blob of cold air that forms under the thunderstorm is known as a cold pool. Those of you who've experienced storms will probably be familiar with this. When you suddenly get a passage of cold air as the storm approaches. This is the leading edge of this cold pool, which is referred to as an outflow boundary or a gust front. And this, as I'll say a bit more about in a while, can be an area where you get really strong damaging winds as well. Some of you, has anyone here witnessed a dust storm? I'm curious. Yeah? Whereabouts? Ah, awesome. Yeah, I think that was a little bit before. What year was that? 2013? 9 or 10. Okay, yeah. Yeah, so I would love to see one of these. So these sorts, I'm sure it's not great once you're inside it. You can't see anything. But seeing this wall of dust approaching would be amazing. They're very common in some parts of the world, parts of the Sahara and the Sahel. But yeah, what you're looking at here is essentially this structure, this leading edge of this cold air. I think this is a photo from Australia, as I believe. I think this is from one of the Bureau of Meteorology's calendars from a couple of years ago. Someone might recognize it. But yeah, essentially this complex, tumbling, turbulent outflow structure is kind of visualized by the fact that it picks up dust if it's moving over the right surface. So yeah, that's on my bucket list to see one of those. Okay, so yeah, to understand a bit more about convection, we need to make some simplifications. And the main simplifications that are made when trying to understand convective storm dynamics are kind of collectively referred to as parcel theory. So I've already mentioned this idea of an air parcel. It's just the idea of having some sort of blob of air with conditions that are distinct from the air surrounding it. And this is a useful kind of way of thinking about how convective storms develop. And we make some assumptions about the properties of this parcel of air. So first of all, we ignore the pressure perturbations. So the dP prime dz thing I showed you earlier, we ignore that. We just assume that everything comes down to buoyancy. So the parcel's motion is entirely being driven by its buoyancy. We also neglect the contribution of hydrometeors. So we assume, generally the assumption made in this kind of analysis is that that the hydrometeors, as soon as they form, they fall out of the parcel. This is not a particularly great assumption, but it allows us to make some useful simplifications. And then another really important one which we neglect is this process whereby momentum, moisture, and temperature are exchanged between the parcel and environment. This is the process generally known as entrainment or detrainment. So this is just mixing between the parcel and environment. And that's really important because mixing means that the properties of the parcel are no longer conserved. And this is very important in all sorts of ways, but again, it's a useful assumption to make. Finally, yeah, we also neglect the effects of freezing and deposition, which again, these are very important. Obviously, above the freezing level, you get a lot of extra latent heat release. And then we also ignore how compensating subsidence in the environment will actually change the environment. So we assume that the environment's kind of static. I say there's a lot of assumptions there, but they do allow us to come up with some neat concepts. Okay, so in terms of understanding convection, can be, it's essentially a form of instability, and so stability analysis is about taking a state, perturbing it a little bit, and seeing whether that perturbation grows with time or sort of dissipates. And so to start thinking about this, we can think of the lapse rates in the atmosphere. So when we talk about lapse rate, we just mean how the temperature changes with height. And there's a few different lapse rates to consider here. So one is the actual environment lapse rate. So this is how temperature, if you take a balloon sounding of the atmosphere, how does the actual temperature of the environment change with height? But then we want to think about our parcel that's rising through this environment. How do its properties change with height? And there's two really important lapse rates here to consider. So the first one is the dry adiabatic lapse rate. So this is the rate at which a parcel of air that is unsaturated will cool as it rises. And it cools because it expands, right? You lift the parcel up, the pressure decreases, it expands, and it does work upon its surroundings, and therefore its temperature decreases. And this is actually a constant. It's just the gravitational constant divided by the specific heat at constant pressure for dry air. And it's roughly 10 degrees per kilometer. So that's nice and simple. Things get a bit more complicated once you have saturation within the parcel. So once the air is saturated, then you're getting latent heat release. So this partly offsets the cooling associated with expansion. And so you get this more complicated expression here, which is essentially the dry adiabatic lapse rate multiplied by all of this. And I realized last night when I was looking at my slides, there's actually a mistake in there. There should be a CP on the bottom of this part here. So if you are particularly keen and want to make a note of that, then do so. But it's not too big a deal. There's lots of different ways I've seen this expression anyway. So it might have been a mistake in the book I got it from, to be honest. Yeah, so essentially the saturated adiabatic lapse rate is less than the dry adiabatic lapse rate. So once a parcel of air is saturated, it doesn't cool as rapidly. And this is really important. This is kind of where we get the energy for these huge thunderstorms. So, yeah, I mentioned stability before and the concept of stability. So just going back to here, the two lapse rates, there are kind of three situations. Well, there's actually five, but three main ones we can think about. So this is considering how the environmental lapse rate compares to our dry and saturated adiabatic lapse rates. So this is a diagram here just showing temperature as a function of height. Here's a rough picture of our dry adiabatic lapse rate. Here's our less steep saturated adiabatic lapse rate. And there are kind of three regions of this parameter space that we can think about. The first, if our environmental lapse rate lies within this region, so the environment, let's say, decreases at this height from temperature here to here, then we say that the atmosphere is absolutely unstable. So what this means is that if a parcel of air is lifted up, it's going to cool at the dry adiabatic lapse rate, but if the environment is cooling at this rate, then at this height it finds itself even warmer than its environment. And so what's it going to do? It's going to continue to rise. So this is an absolutely unstable environment. Whatever happens, if you perturb that parcel, it's going to keep going up. But this is actually a really rare situation in the atmosphere. The only place where this typically happens is right next to the surface. And the reason for that is because that situation can't persist naturally, right? If that's the situation, then there's always, wobbles in the atmosphere. There's various little perturbations. So if you have an absolute unstable situation, it'll very quickly mix out. The only way this persists near the surface is because the sun is constantly heating the surface. And so you can actually get a maintenance of this kind of critically, absolutely unstable state. The other extreme is that we're in a situation where the atmosphere is absolutely stable. So if our environmental lapse rate lies to this line, then even if our parcel of air is saturated and it rises up to here, let's say, it's going to find itself cooler than the environment. And so it's just going to want to sink straight back to where it came from. So in that case, we're not actually going to get any convection whatsoever. But this is the interesting one. This is the case where the environmental lapse rate lies between the dry and saturated adiabatic lapse rates in this yellow region of the parameter space. And in that case, we see that if the parcel's dry and it rises, then it's going to be cooler than its environment. But if it's saturated and rises, then it's going to be warmer than its environment. So the parcel, or rather, I should say, the lapse rate is described as being conditionally unstable because it's unstable provided the condition that the parcel of air that you're lifting is saturated. And this is a common situation in many parts of the world, and this is what one of the key ingredients to have convection of any form. You need some region of the atmosphere where the lapse rate is conditionally unstable. And I've mentioned here there are two other states that have to be mentioned, which is that, if the lapse rate happens to fall exactly along the dry adiabatic lapse rate, then the atmosphere is said to be neutral, or if it lies along the saturated adiabatic lapse rate, then it's moist neutral. Lying along the dry adiabatic lapse rate is actually fairly common in the boundary layer. Some of you who've seen balloon soundings will be familiar with this idea that the temperature profile will roughly follow a dry adiabat. And yeah, that's just because there's always this mixing in the boundary layer, so it tends to create this neutrally stratified situation. Okay, so with these concepts, then we can introduce a few other terms which are important for thinking about convection, and in particular the initial kind of development of convection. So there are three height-related things to consider here, these three levels, and then two energy variables. So first of all, we have our lifting condensation level. So that is if you take a parcel of air, for now let's just consider taking a parcel of air that's initially located at the surface. At some height, so as it rises through the atmosphere, its temperature is then going to decrease, but the amount of water vapor within that parcel, assuming it doesn't mix with its environment, is going to stay constant. So as a result, at some level, it's going to become saturated because the capacity of the air to hold that water vapor decreases as its temperature decreases. So the height at which this occurs is known as the lifting condensation level, LCL. So then, potentially at the LCL, but also potentially some height above that, it's going to actually become buoyant. And this really depends on what we said before about conditional instability, where that occurs. So the parcel may be saturated, but if depending on what the temperature profile is below that level, it may not actually be buoyant. So at some further height, higher up, it'll actually become positively buoyant, and this is called the level of free convection. So then you've got your parcel, it's now buoyant, it's rising through the atmosphere freely convecting under the effects of buoyancy. At some height, usually, at the very least, at the tropopause, it's going to reach a level where it's no longer buoyant. This may well occur at a higher level, but it certainly can't occur much above the tropopause because temperatures start to suddenly either stay constant or increase with height there. So at this point, it becomes negatively buoyant again, and so it'll stop rising. So many of you have seen, your typical kind of thunderstorm cloud. We'll see at the top of the cloud it kind of spreads out laterally and forms this anvil feature. That's because the air's become neutrally buoyant. It's hit some sort of stable level, probably the tropopause, and the air is consequently spread out. So this is referred to as the level of neutral buoyancy. I like this term because they're all L something or other, but you may also see it called the equilibrium level. It's the same thing, essentially. And then we've got these two energy variables. So I'll actually start with the bottom one with CIN. So there's a certain amount of energy that's going to be required for the parcel to have in order to reach the level of free convection. And that's what's measured by the convective inhibition. So the smaller the convective inhibition, the more likely it is that you're going to get storms. And then we've got the convective available potential energy. So this is the energy available to the parcel as it ascends from the LFC to the LMB, and I'll illustrate these concepts in a minute. But essentially, the bigger the cape, the more intense your thunderstorms. So yeah, how many people here are familiar with these sorts of diagrams, SKU-T diagrams? Most of you, okay, good. Who hasn't encountered these before, out of interest? Yeah, okay, so, and who feels really, really comfortable with them, even if you haven't encountered them or have encountered them? Yeah. So they're a bit of a nightmare to look at initially, but it's not as bad as it looks, essentially. There's a lot of lines on here. But essentially all we're plotting, the main thing that we're plotting is temperature versus height, effectively. But instead of height, we use the log of pressure because pressure is actually a thermodynamic variable rather than height, so it can be related to temperature and moisture and things. And then rather than plotting exactly temperature on the x-axis, we plot the temperature axes at 45 degrees. So that's what you can see in the two grey lines. So we've got constant lines of pressure along here, and lines of constant temperature at a 45-degree angle. The only reason we do that is so that the profile is tilted roughly upright. If you've ever tried plotting just temperature versus height or temperature versus pressure, it leans right over like this. It's actually really hard to see the structure. So the only reason we do that is just to make it look a bit nicer. It just makes it easier to interpret. And then there's a few other lines on here. So these blue lines here are our dry adiabats. So if you have a parcel starting here at 1,000 hectopascals and it's unsaturated, it is going to follow this line. We also have these green lines here. These are our saturated adiabats. So the parcel, once it's saturated, is going to follow these lines. And then the final thing we have on here are these pink lines. These are lines of constant mixing ratio. So this is just a measure of the amount of water vapor in the air. So yeah, there's a lot going on, but these are really useful tools because you can say a lot about what's going on in the atmosphere with them, or at least you can once you've actually overlaid a sounding. So that's what we do. So on these diagrams, you just plot, you've got your balloon sounding, which measures temperature, humidity, and pressure as it rises through the atmosphere. And then you can just plot those points on here. So this thick black line is the temperature profile, and the dashed thick black line is the dew point temperature profile. And then there's one other thing I've plotted on here, which often gets left out of these, but it is really important, and that is the virtual temperature profile. So remember before I said that buoyancy is defined in terms of virtual temperature. The moisture perturbation does really matter near the surface, and you can see that because there's this gap between the temperature and virtual temperature profiles, and that can make a big difference, actually. So it is important to include that, even though often it gets left off. So we can see some of the parameters I mentioned before on here. So what we've done here is we've taken a parcel of air from the surface. So this thinner black line is the profile of virtual temperature, again, not temperature, of the parcel of air. So it's ascending from the surface. At this point here, at our LCL, it becomes saturated. So it initially follows a dry adiabat. Once it becomes saturated, it then follows the saturated adiabat all the way to the point where it reaches the LNB. And then we've got our CAPE and CIN areas. This is actually not a great example. It was just a sounding that I happened to have lying around. But it's not a great example because actually, while we have our LFC here, there's actually another LFC at the LCL, which may seem a bit weird. But this can happen. It's not uncommon, right? So essentially, the parcel gets to its LCL. Oh, look, it's buoyant, so it'll start to rise. But then there's a layer above where we've got this inversion in the temperature profile. The temperature suddenly increases with height, and so we have a layer with a bit of CIN in it. But this can actually be really useful, in fact. So having some amount of convective inhibition can actually prevent storms from just going at the start of the day. So in the tropics, where there's not much convective inhibition, you may get convection just firing as soon as the sun comes up almost, or early in the day. But with severe convection, it can help to have a bit of CIN because it prevents convection from going off early in the day, and so instability and other conditions can kind of build up to a point where they're kind of capable of creating severe weather. I think I won't say anything more about that for now. Okay, then, yeah, so then we need to think about processes. So how does the environment actually create CAPE, and how does it destroy CIN? Because that's what we need if we're going to get storms. So there's a few things here. I don't really want to go through this equation in any detail. This is just essentially you can take your temperature equation and you can manipulate it in such a way that you get an equation for how the environmental lapse rate, so I represented that here by a small letter gamma, how the lapse rate changes with time. And this is really critical for how an environment becomes conducive to convection. And there's lots of different terms in that. I wouldn't worry about most of them. The really important one, the one that has the most effect, is this term here. This is just essentially, this is differential advection of temperature. And all that means is that if you advect cool air above warm air, you're going to get an increase in the lapse rate, right? That's all this term is essentially saying. And that's shown in this schematic here. So if you have an initial sounding where the temperature is not decreasing much with height, but then you advect cold air above warmer air, then you're going to get a steeper lapse rate. And that is going to enhance your CAPE. It also may potentially reduce your CIN. And this equation is often kind of sold as sort of explaining how instability builds up in the environment. But there's a lot more to it than that, in fact. And that's illustrated by these schematics here. So you can get a few different processes that can help to enhance your CIN. So we've got a kind of typical convective storm environment here, from the US at least. And there's three processes highlighted here. So one is if you get some sort of cooling around this level, then that's going to remove your CIN. It's not going to act to increase CAPE much, but it's going to do enough that you might actually trigger storms at some point. Then two other effects. One is if you moisten the boundary layer. So if you've got, you know, a good example would be for somewhere like down in Melbourne where storms aren't all that common. If we start to advect air in from up sort of Sydney and the Coral Sea, then we increase our boundary layer moisture. And as you can see, that can lead to a substantial increase in CAPE and a decrease in your CIN. And likewise, if we warm the boundary layer, we can increase CAPE and decrease CIN. So yeah, all these processes are pretty important in terms of actually setting up the environment for convection. And then there's a final ingredient for convection which I haven't mentioned so far, and this is actually triggering. So I said before that it takes a certain amount of energy for a parcel of air to reach its level of free convection. Where does that actually come from? How do we actually trigger it? And there's a variety of processes that can do that. A lot of them, you'll notice, are really various forms of atmospheric boundaries. So what we're looking at here, so what I mean is fronts, dry lines, convergence lines, sea breezes, and outflow boundaries. These are all boundaries between air masses with different characteristics. And the main reason why these are favorable areas for convective initiation is because they're locations where you've got convergence and you've got lifting. And that lifting is usually what it takes to kind of push parcels of air to the LFC and kick convection off. But there are other processes as well that can set it off. So you also got gravity waves. When a gravity wave passes through, you get a sort of vertical displacement of the parcel. That might be enough to set convection off. You also have upslope flow over orography. And then horizontal convective rolls. So these are kind of, if any of you have seen cloud streets on a sort of summer day, these are just basically rolls, counter-rotating vortices that form when you have a bit of wind on a day where there's sort of a bit of instability about. But actually, it turns out that the best conditions for convective initiation are when two or more of these features come together. So that's what the schematic on the right is illustrating. So this is originally taken from a case in Florida where you had a sea breeze moving inland, and you've got a scent along the leading edge of the sea breeze front. But then you've also got these horizontal convective rolls in the environment. And where these features coincide, you actually are more likely to get convective initiation. So again, it's the combination of these procedures that can be really critical to convection. And I'd actually say this is still probably the biggest problem in trying to forecast convective storms. A lot of the processes that supply CAPE and remove convective inhibition occurring on kind of synoptic scales. You know, it's kind of the geostrophic wind advecting about areas of high temperatures and high moisture and things like that. But convective initiation occurs on much smaller scales, typically mesoscales or maybe even the storm scale, and it's really, really hard to represent. And to a large degree, it's kind of a stochastic process. So it's really convective initiation why we need to run ensemble models to be able to actually forecast convective storms in any reasonable way, because it's just so chaotic and random that with a single realization, you're just not likely to capture this. So yeah, this is still a big problem, and I think it's still an active area of research, but yeah. Okay, so now we're finally getting on to sort of talking a bit more about severe convection. So for severe convection, you really need one extra ingredient, and that's vertical wind shear. So what we mean by vertical wind shear is just changes in wind speed and or direction with height. And this has kind of three important effects on a storm. First of all, it separates the updraft and downdraft of the storm. So as a general sense, there's a lot of complex factors that affect particularly downdraft dynamics. But as a general rule, as you increase the shear, you tend to find that your precipitation and your downdraft associated with that are kind of separated from the updraft. And if your downdraft falls through your updraft, then it just kills it and it's game over, the storm's done. So increase in shear can help the storm in that way. It also, at low levels, can prevent the outflow from undercutting the updraft. So if the outflow spreads, you have an initial storm, the outflow spreads out, it stops warm air from being able to reach the storm and supply it. So again, vertical shear can help with that. And the final effect, and this only really becomes important in supercell storms, is that through a variety of complex processes, vertical shear can promote development of these vertical perturbation pressure gradients. So you can get a situation where your updraft isn't just being driven by buoyancy, it's actually being augmented by these additional effects. And I say this is important in supercells. So we generally think of this kind of sliding scale of convection, which ranges from sort of simple single cells up to what are termed multicells and all the way up to supercells as your shear in the lowest sort of roughly 6 kilometers of the atmosphere increases. And yeah, I'll talk a bit about what these different types of storms are. So first off, the kind of most basic and probably least severe type of convection is single cell convection. This is kind of thought of as, it's sometimes referred to as sort of pulse convection, and it's also referred to as ordinary convection. This is very typical in places like the tropics where there's not a whole lot of wind shear about. So in this case, you just have a single updraft. You don't get any kind of organized initiation of new convection, and as a result, these storms tend to be fairly short-lived. So many of you will have seen these storms on hot summer's day where they just go up. You maybe get a few rumbles of thunder, it dumps a load of rain, and then it evaporates, and you might just be left with a sort of anvil hovering at upper levels, and that's all there is. But it's worth emphasizing that these storms can be hazardous. And in particular, they can produce damaging winds in the right conditions, known as microbursts, which I'll talk a little bit about in a minute. And you can also get weak tornadoes associated with them. So probably people, especially people living along the East Coast, might have seen waterspouts. Many people have seen them. They're quite common along the coast. And I'll say a bit about them in a minute. But yeah, they're typically associated with these sort of fairly small, innocuous showers. So the next in our as we increase vertical wind shear, the next step we get to is multicell convection. So now we're in an environment where we've got moderate vertical wind shear, 10 to 20 meters per second wind change over the lowest 6 kilometers. And in this case, what we're actually dealing with is not a single convective storm, but multiple convective storms that are interacting with each other. So they tend to consist, in this simple form at least, they consist of multiple updrafts that are different stages of their life cycle. And what's happening is the outflow of one storm is initiating a new storm in a sort of sequence which can last for several hours. And typically this occurs on some preferred flank of the storm. So this is illustrated in this schematic where you've got these 4 cells at different stages of their life cycle. The most mature cells are producing precipitation. That precipitation is falling, it's evaporating, it's creating a cold pool, which is spreading out, and then you're getting lift along the outflow boundary, which is triggering new cells. And this process can persist for hours at a time, potentially. And this is a really nice photograph, actually, showing, I don't know, I feel like the schematic was almost based on this photograph, but this is the most sort of famous photo I found of a multi-cell storm where it just kind of perfectly fits that, that conceptual model. So these storms, again, mostly they're non-severe, but they can produce some hazards. So they may produce some small hail. Well, actually, as I'll say in a minute, some more organized systems can produce larger hail. They can produce damaging straight-line winds. They may produce tornadoes, typically not very strong ones. And a really important one with these types of systems is heavy rain. So if this process is occurring again and again in the same location, then you may get a situation where you produce rain that can lead to flash flooding. Now there's a second kind of class of multi-cell convection, which is referred to as MCSs. This is actually kind of a sort of, it's more related to the scale of the system. So if the system extends over 100 kilometers in one dimension, then it's classed as an MCS. And then there are various subcategories of MCS. So some of you, the term squall line is sometimes used to refer to some MCSs, although it's a bit of a catch-all. And another type is bow echoes. But in this case, it's a little bit different from this schematic we showed before, where you've just got kind of a few cells with influencing each other. In this case, you have a kind of coherent line of convection. So here we've got an entire line of mature convective storms. And new storms are being initiated ahead of it. So we can actually see this as a radar display. We can actually see this thin line here. This is actually demarking the gust front of the storm. And the reason we can see it is because it tends to capture insects that get kind of caught in this region of convergence along the gust front. It's really useful, actually. Like, insects are a really great tracer in some instance of the air. So they can be good. Although I've never actually witnessed them. I've experienced a lot of gust fronts, but I've never actually experienced the insects coming through, so I assume they must be at a higher level or something. Anyway, yeah, so you tend to have this kind of intense line of convection, and then you may have a region of weaker precipitation called the transition region, and then behind that you have heavy stratiform precipitation. And generally this system will be moving in this sense, so towards the southeast in this particular instance, although the orientation of the system will vary, of course. And these storms, they're particularly known for producing damaging wind gusts, and that's associated with a few different processes. One is the fact that you've just got this kind of organized cold pool, and that's associated with kind of strong gusty winds. But you can also get this rear inflow descending into the system from the rear. So this is like looking at a cross-section cutting through this storm from northwest to southeast. And so you've got this region of intense convection at the leading edge of the storm, being fed by new cells developing on the gust front, and then you've got this area of broader sort of stratiform rain behind. And where you get this descending air coming in from the rear of the storm, that can also lead to really strong surface winds. And one instance where this can be particularly severe is when you get a bow echo. So this is when this structure actually develops a kind of bowing form where the rear inflow accelerates in the center of the storm, and then you get this kind of bow-shaped structure essentially. I'd say there's more complex dynamics to how these things actually form. But yeah, these can be associated with really strong wind gusts. And you'll notice in this case that the bow isn't symmetric. So while initially it might be fairly symmetric, over time you're getting this asymmetry where you've got a more pronounced, what's referred to as a comma structure on the northern side. This is a northern hemisphere feature. In the southern hemisphere, this feature would be on the south side, and it's because of the effects of the Coriolis force, which over time favor one end of the line over the other. Okay, finally, my favorite, supercell convection. So this is the type of convection that will occur in environments of really strong vertical wind shear. So typically you have more than 20 meters per second of wind shear over the lowest 6 kilometers. And these are a really special type of storm. So they consist of just a single updraft, but unlike our ordinary single cell convection, they don't just they don't just die straight off. This is a single updraft that can persist sometimes for hours at a time. And it's because they have this really unique structure which allows them to have continuous supply of inflow flowing into the storm without it being cut off by the downdraft. So this is kind of a schematic looking down at the storm effectively. So what's shown in the green here is what you might expect to see on a radar display. Again, this is northern hemisphere centric. In the southern hemisphere, generally the storm will be flipped in the vertical axis, although you can get both types in both hemispheres, but I won't go into that. And essentially you have this interesting structure where you have an updraft located here, and then your downdrafts are kind of wrapped around it. It almost, Michael Reeder commented to me at one point that how similar this looks to a kind of frontal wave cyclone, and it does in some ways, although it's at a completely different scale, as you can see from here. But yeah, essentially you've got this organized structures whereby the outflow isn't cutting off the updraft, and they are able to stay separated, and let's say the storm can persist for hours at a time. And these storms are responsible for almost all of the large hail. By large hail, I mean hail that's sort of kind of golf ball size and bigger is associated with these storms. They can be associated with damaging straight line winds as well. In fact, while generally we think of straight line winds as being associated with the outflow from a storm, some supercells can actually have inflow that is so strong that it can cause damage. That's rare, but it can happen. And the reason for that is because these storms have these vertical perturbation pressure gradients. So this is a picture. If you imagine if you'd taken a photograph looking towards the storm here, that's what this is essentially showing. So we've got the forward flank downdraft, the FFD, on the right-hand side of the image. This rear flank downdraft is supposed to be behind the tornado, which is just in here, and then this is your main updraft. And what's special about the supercell updraft, as I say, is that it's not just generated by buoyancy. It also has these vertical perturbation pressure gradient effects. So another way of saying is that the air is not just rising because it's less dense than its surrounding. It's also actually being sucked up by the storm. And so you actually get these really interesting and quite beautiful structures in supercell storms. you'll notice, this isn't a great example, but if you Google Supercell, there's lots of amazing pictures. But you can see this kind of turbulent structure above. This is the structures we typically expect with buoyant convection. But at low levels, we actually have sort of more kind of, it almost looks like an orographic cap cloud or something like that. You know, it's kind of stratiform and smooth in nature. And that's where this air is actually being sucked up by the updraft. So these storms, as I said, can produce straight line winds, and they're responsible for pretty much all of the strong tornadoes. So that's EF2 tornadoes and above on the enhanced Fujita scale, which goes from 0 to 5. And they can also, in some instances, produce heavy rainfall. You could do a whole series of lectures on the dynamics of these storms. The main thing to know is that essentially what characterizes supercell is the fact that the updraft is rotating. And the updraft rotates because you draw horizontal vorticity into it. And the horizontal vorticity is created largely by the fact that the wind is changing in speed and direction with height. But say, if you want to know more about supercells, come and talk to me. I can probably talk all day about them. Okay, so let's talk a bit. We've got a little bit of time left to talk about the actual hazards themselves. So starting off with hail. So as some of you may already be aware, kind of the basic process behind hail is that you have some sort of ice embryo, so you have a small particle of ice, and this is large enough to kind of start falling with respect to the small cloud drops around it. And then if you have lots of supercooled cloud drops, so this is cloud drops that are, this is all happening above the freezing level, but the cloud drops are being lofted by the updraft, and they're not actually freezing instantaneously. And so if this ice particle is falling with respect to the supercooled drops, then as it falls, it tends to collect them, and they freeze on its surface, and so it grows over time. So that's what this schematic is essentially illustrating. But obviously, to get really big hail, the biggest hailstone ever recorded, I think it was 13 centimeters in diameter, something like that. Maybe even bigger than that. I'm trying to think. Sort of grapefruit-sized hail is the term that's used to. Yeah, that was in Nebraska, I think, back in 2011. Was the biggest, but it's quite likely that there may be bigger stones out there. It's the odds of them being observed. But yeah, to get these really massive hailstones, then, can you imagine trying to suspend something of that size within a storm? You need a really strong updraft. So these things tend to form in environments with large cape. But there's also this idea, and I think this is something, I feel like this still isn't that well understood, because you can't really fly instrumentation through a storm that's got hailstones the size of baseballs and grapefruit and that floating around in it. It's really hard to measure, so I think this is still a bit of a mystery, exactly how these storms form, how these hailstones form. But the general idea is that there must be some sort of recycling process happening. So you get a hailstone that's sort of developing. It gets big enough that it starts to fall, or it gets ejected from the updraft. But then at some point it re-enters the updraft and kind of gets cycled through a few times. And part of the evidence from this comes from the fact that if you get a hailstone, you cut it open, you'll see kind of layering structures in there, which suggests the layering is associated with the fact that the hail's grown at different temperature ranges. And so this seems to suggest that there is some sort of cycling process. But yeah, essentially, it's going to take a lot to keep these stones suspended, and this is actually illustrated here. So this is just a simple equation for the terminal velocity of a hailstone. So it's proportional to the square root of the diameter of the stone. And there's some other terms in here, one of them being this drag coefficient. So what's plotted here is this terminal velocity as a function of hailstone diameter with a few different drag coefficients. The drag coefficients essentially take account of the fact that some hailstones are really smooth, and so they're not as affected by air resistance, whereas some hailstones are really spiky, and so they have more drag exerted on them. But you can see that once you get to hailstones that are sort of getting up to kind of 10 centimeters, you're getting up to terminal fall speeds of 50 meters a second. So to keep a stone like that elevated in the storm is going to take a seriously powerful updraft. But updrafts this strong do occur, particularly in supercell storms. Okay, so that's a little bit about hail. I've already mentioned a little bit about straight line winds. The reason we say straight line winds is to distinguish between them and rotational winds, i.e. tornadoes and the like. So straight line winds, there's kind of two types we think about here. So one is ones that are just associated with typically an isolated downdraft. These are referred to as downbursts, or if they're really small in horizontal scale, they're referred to as microbursts. This is an amazing picture. I believe this is from Arizona of a microburst. They're quite common in this environment because what they really acquire is a high cloud base with very dry air below. And what that favors is a lot of evaporation of rain as it falls through, so the air gets cooled massively and descends really, really rapidly. And these events can be particularly hazardous to aircraft, particularly in cases where there may not be a precipitation shaft visible. So in this case, this is what's known as a wet microburst because the rain's actually descending all the way to the ground. But in very dry environments, the rain may actually evaporate altogether. And the only thing you'll know about the downdraft is when it hits the ground and kicks up a load of dust, or when it blows your car over or something. And I say, yeah, they can be really dangerous to aircraft because if a plane's flying into one of these things, it may initially experience some sort of lift as it is into this kind of ascending region at the leading edge of the gust front. And so the pilot may think to adjust to account for the fact that the plane's now tilting upwards, but then suddenly it experiences the full force of the downdraft, and there have been a number of aircraft incidents that have been associated with these effects. Warning for these events is, it's a real concern for airports where planes are coming into land like this. The other type of straight line winds are these ones associated with squall lines and bow echoes, and there's kind of, as I said before, two effects going on here. One is this just sort of downdraft effect where you get kind of surging air. Many of us would be familiar with that with some of the sort of convective lines that come through Melbourne, particularly in the summer. And then you also get this effect of the rear inflow jet. So what we're looking at here is a radar image of a bow echo. Here's your convective line here. And then this is the Doppler wind image. So the radar's located here. What these colors are indicating is the strength of the flow either towards or away from the radar. In this case, these blue colors are showing flow towards the radar, and it's getting up here in excess of 30 meters per second. So this is really strong air that's moving into the back of this system, descending, hitting the ground, and spreading out. These things can be pretty damaging. Okay, finally, not finally, actually, tornadoes. So these are, I consider these the most fascinating phenomena. As I say, they're predominantly associated with supercell storms, but it's important to realize that while a supercell storm is characterized by the fact that the updraft rotates, it's not actually just an extension of that rotating updraft towards the surface. There's a lot more going on with this, and this is still a really big question in mesoscale meteorology, is how do tornadoes form? In the last couple of years, there's been some really, really interesting studies that have come out about this, but it is still a bit of an open question. I don't really have time to go through all of this. There's just a few points I want to make. So one is that studies have shown that in terms of the ingredients that favor tornadoes, there's kind of two important factors. One is if you've got a low LCL, or in other words, if you've got quite a humid boundary layer. This seems to be important because it prevents you from getting a really strong downdraft. So I mentioned before when I was talking about downbursts, if the boundary layer is really dry, you get a lot of evaporation, you get a really intense cold pool. That doesn't seem to be very favorable for tornadoes. You don't want the cold pool to be really intense, otherwise it seems to kind of cut off the supply of air to the tornado. At the same time, you also want really strong shear in just the lowest 1 kilometer. And actually, recent studies like this one here have actually started to indicate that it may even be the wind in just the lowest 500 meters above the ground that's really critical for this. So this is a composite of hodographs from observations from the Vortex 2 field campaign that took place a couple of years ago. And what we're looking at here, the red is a composite for tornadic supercells and the blue is a composite for non-tornadic supercells. And the only really significant difference between these two is just this little kink here, which is occurring in the lowest few hundred meters above the ground. The work that these guys did has shown that this is actually really critical to whether or not you get a tornado. So it's really amazing that, that the winds in just this lowest level can matter quite so much. And it does affect the kind of predictability of these storms. Yeah, I don't think I'll say any more about that for now. And then, so yeah, it's also worth distinguishing between tornadoes that are associated with supercells, so these are referred to as mesocyclonic tornadoes, and all other tornadoes, tornadoes that are associated with other forms of convection. So this includes things like water spouts or land spouts, things like that. And in this case, the mechanism is a bit different. So whereas in this case, there's kind of the complex dynamics of the supercell going on, and you need downdrafts, and you need vorticity rivers and all sorts of other things. In the case of these storms, all we essentially have is some sort of boundary. Often in the case of water spouts, this will be a land breeze boundary, so just offshore. I saw some myself, I think it was at Byron Bay or something, and just happened to look out to sea and see a load of water spouts out there. And yeah, essentially you've got some sort of boundary between air, you get these kind of instabilities on it, they kind of roll up and you get a bit of vertical vorticity. This gets stretched underneath a cumulus cloud, and you get some sort of, you get a water spout or a land spout. And actually, it's quite common to see multiple of these things at once. So there are parts of the world off the coast in regions of Florida, say along the east coast of Australia, and parts of the Mediterranean Sea where it's not uncommon, particularly in the early morning, to see a line of water spouts offshore. And yeah, that's just because they tend to form along these boundaries. Okay, I've got 5 minutes, 10 minutes? I can't remember when we started. 5. So finally, heavy rainfall events. To say it's important to realize that these are a bit distinct from the other hazards because hydrology plays a big part. But in terms of the meteorology, things can be kind of summed up by this equation. So this is for those of you who like your equation simple. This is equation is sometimes referred to as the first law of quantitative precipitation forecasting. So all it says is that essentially the largest precipitation totals occur where the average rain rate is highest and the duration is highest, so where it rains hard for a long time. This is a very simple relation, but it nicely captures the effects we need to think about. So what are the ingredients for heavy precipitation, and how do we get that precipitation occurring for a long period in the same location? So one method we can do that is if we've got a multicell convective system which is just kind of sitting in the same place. So the individual cells within the convective system might be moving at this speed, but then if new cells are developing upstream at roughly the same rate, then the system itself isn't going to move very much. And this is actually a really common situation in which you can get really heavy precipitation events in all different parts of the world. Another factor that's really important can be orography. So if you have air approaching a steep terrain barrier, then you may get repeated triggering of convection along that barrier. And there's lots of examples of that from the Mediterranean Sea. Yeah, and there are a few other mechanisms as well, but those I think are the key ones. Okay, finally I want to say a bit about severe convective storms in Australia. So most of what I've talked about before, there's a lot of research been done on this in the USA, but this is a really big deal in Australia. So, for example, if you take the 13 disasters in Australia that have cost over $1 billion Australian dollars, 6 of those were hailstorms. And actually, the number one was a hailstorm, the Sydney 1999 hailstorm, which, if you scale the dollars to 2015 value, caused over $4 billion worth of damage. So there's a paper by Schuster et al. Where they looked at this particular event, and essentially this supercell storm tracked right over the CBD and dumped some big hail, sort of cricket ball size hail. So these events are really, really costly, even though they're generally not associated with fatalities, I guess mainly just because people can find shelter in most cases. Australia also does get tornadoes, so this is a case from near Kiama in New South Wales, where there were actually multiple tornadoes. This is, you can see a line of kind of flattened vegetation where this tornado moved inland. I don't think this was a supercell tornado. This was probably a non-mesocyclone tornado. There's a nice case study been written on that, which will be coming out in BAMOS soon, I think. And then there are other cases. So this is the Brisbane hailstorm from 2014. These were some of the hailstones from that. I think this was about an hour after they'd landed. So this is them having melted quite a bit already. And then this is the Gap windstorm from Brisbane. So all I want to really emphasize here is that these events do happen in Australia, and they are really critical. they're not just an American phenomena, even though if you read the literature you might think as much. And there are lots of other parts of the world as well where they do occur. I think in the interest of time, I can very briefly mention climate variability. So this is just to say that climate variability is important for these events, but it is difficult to tie down the effects of climate variability and climate change on these events because they are so small scale, and also because our reliable records of them don't go back that far. A lot of events get missed because they happen in areas where people don't live. You know, it's harder for a tropical cyclone to go missed. If it makes landfall, someone's going to know about it. But with these types of storms, they sometimes occur in very remote areas. But nevertheless, some work has been done and has shown that, for example, that El Nino does affect severe weather. So this is using an index of hail occurrence and an index of tornado occurrence and comparing situations during El Nino and La Nina. And we see an enhancement of probabilities over the sort of southern Great Plains. And there's a similar sort of stuff that's been done. So all of this is by a guy called John Allen, who was a PhD with Kevin Walsh at Melbourne. He's now based in the US, but he's done lots of work on this kind of stuff. And he also showed that, that in Australia there is an enhancement of severe probabilities in El Nino, in kind of Western Australia, and in La Nina, in kind of southern Victoria and along the Queensland coast. I've been living here since 2014, and I've been waiting for a really good La Nina, because apparently that's when Victoria gets all its good storms, but I'm still waiting. Okay, finally, climate change. I think this is a really fascinating area, and while I'm not hugely brushed up on the literature on this. I'm surprised that there aren't more studies on this, because I think there is really interesting science to be done, and so maybe this is something that you guys can be thinking about. So, as I say, it's a problematic area because, as we've already heard, the climate models definitely can't simulate these things, right? These are events that are occurring at a scale of a kilometer or less. There's no way we can represent them with our current climate models. But we can say something about the environments that favor these events. And so that's what some people have tried doing. So John Allen did some of this work in Australia early on. He was looking at 2 climate models and looking at how the frequency of environments that are favorable to severe convective storms would change in the future. And he found actually that there did seem to be a robust increase in the frequency of these environments in the future along the kind of east coast of Australia. And this mainly seems to be associated with an increase in CAPE. So in future climates, it seems that the atmosphere becomes more unstable, largely, I think, through the fact that you get more moisture at low levels, which acts to enhance CAPE. In actual fact, at the same time, your vertical wind shear generally seems to decrease, and this is predominantly associated with the fact that the equator to pole temperature gradient is decreasing. And so through baroclinicity, we're actually getting less vertical wind shear, but that effect seems to be overpowered by the fact that there's more CAPE. So there's only one real study aside from this one that I've really seen that has looked at this question in any more detail, and this was Diffenbauer et al. So this is from PNAS a few years back, and this is a really cool study. Again, USA focused, but they looked at when you kind of whether you get some sort of emergence of a signal for enhanced severe convective storm risk in a future climate, and they actually found that this actually emerges before we get to 2 degrees warming above pre-industrial levels, at least during the shoulder seasons of spring and autumn. And again, they found that this increase is largely associated with an increase in CAPE, and there's a decrease in the shear. But what they actually found, this is interesting because sort of people have said, oh, well, the shear is going to decrease in the future, so maybe we won't get as many severe convective storms. But they actually looked into this further and found that actually the days when shear decreases tend to be the days when CAPE is weak anyway, so they're not favorable to convective storms. On the days where you have a lot of instability, actually, the shear doesn't seem to change too much. So this suggests that we are going to get an increase in severe convective storms in the future. But to be honest, yeah, I haven't seen a whole lot of these studies, and I think it would be really cool to see a lot more done in this space. So I guess that's something for you guys to think about if you're interested in this kind of stuff. So yeah, I've got some references here. If you're interested in this kind of stuff, I'd really recommend this textbook, Mesoscale Meteorology in Mid-Latitudes by Mikowski and Richardson. It's where, as you probably noticed, half the figures I showed came from, and it's a really, really excellent book. So yeah, seek that out if you're interested in more, or talk to me in the break.